So there is one question which I want to address, Abhijit asked, which is S gen exactly zero when you have only evaporation? No, it's not. Actually, it is.
With the derivative.
Yeah, derivative. So it's actually a coarse-grained entropy, and all the proofs of the GSL that we are doing in the order G approximation. So we are doing perturbative. Every GSL proof is perturbative. So it's not back reaction of the fields on the black hole is not taken into account. It's just small fluctuations. You're still in some background, which is the Schwarzschild background, and then you have gravitons, and you can include the ADM mass and all that. So it's, yeah.
So what was the question?
The question was, is generalized entropy exactly zero if you just going to consider black hole evaporation?
Constant with the derivative.
Definitely not.
Yeah,
In fact,
that's
those were
not.
the first calculation, for example. Yeah, absolutely. It's just because, what happens physically is that as you make longer and longer, the invariant cutoff which you have to impose, if you keep that fixed in physical distance, in terms of the wavelengths of modes which make up the vacuum, it becomes shorter and shorter. So you can do the following calculation in 2D, which is the old stuff, for example, which is you can just produce a pure black hole, out of pure state and let it evaporate and compute SGen.
So SGen is area plus the entanglement entropy outside, right?
Outside. And because the entanglement entropy has a cutoff, but that cutoff has to be thought of properly. If it's thought of, if you think about it properly, keeping the invariant cutoff in physical distance fixed at the horizon, then you find that the effective contribution goes up and up, with time. And that's one way to see the Hawking puzzle.
Meaning it goes faster than the area.
Yeah, it goes faster than the area, or you can even do a toy experiment where you keep the area fixed by feeding in pure, you feed in a pure state, at some constant rate. Area will even stay fixed. SGen will go up.
Yeah,
that's like the simplest. This is like, sorry to say this, but in that paper, Prestel, Strong engine, this is the kind of things we did.
Yeah, and it's one way of saying this is why the black hole evaporates, because it increases it. Because the evaporation process goes to a higher end. Is that right?
But this is
Here she was trying to distinguish coarse-grained.
Yeah,
fine grained. So,
This is that practice that is generalized as coarse-grained.
Cost grain, yeah. So cost grain entropy should increase.
but the SGen, then one gets a little, okay, anyway.
No, I mean the classification of coarse-grained and fine-grained, which you see in Malachin as value for that. That was the question. Yeah, so it's coarse-grained.
Yes, he calls including the entanglement coarse-grained.
Yeah.
just by
Yeah,
saying it is this entanglement doesn't make it
I
fine.
don't know what I would call it, but anyway, it's
Just saying that SN is not fine grained. It's not making it fine.
Yeah.
But did you guys say the same thing? I thought you were saying something like you're leaving something out of the
I'm sorry.
I thought your answer was something like you're leaving out the effect of you're leaving.
No. It is coarse-grained. That's what
Yes, but
yesterday.
is it to do with something moving down the cutoff or because you're neglecting that reality?
No, I'm just saying that in all the GSL proofs which everybody does, they are perturbative in G. In the G going to zero limit.
You could say, I think perhaps this is what you're saying, it's coarse-grained in the sense that this is generalized second.
Yeah.
Yeah.
Okay, so let me just continue from where we stopped last time. So what?
Suneeta, one question that to you, following the discussion from lunch yesterday. I wondered, so what I understood from the end of your lecture, your very nice lecture yesterday, was that there were all the trace modes inside. And then there was this Gauss law, which told you that the trace modes were the difference between or sum of these two Hamiltonians of the two boundaries. Okay, so, but there was one degree of freedom that was not determined.
Yeah, there was only one extra degree.
Now, I want to understand that statement classically first, before looking at it what you can. So, are there so I suppose is that just the mass of the black hole? Oh, sorry, okay, so let me ask. Presumably, there's a classical manifold of solutions. Say I start with a black hole, and now I look at excitations around that black hole. Of course, one way to put excitations is to put traces here. That will create that will determine the difference of some of these two energies. Now, is there a classical way of exciting the one that is not created by these traces? Gravitons. So let's say you have gravitons inside. Let's choose a convention. Let's say H minus H, H right minus H left. H right minus H left is energy of gravitons. So if I excite some number of gravitons, that tells me what H right minus H left is. It does not tell me what H right plus H left. Okay, so now I wanted to understand classically the way of exciting H right minus H left is by adding gravitons. What is the classical way of exciting the other? Is that by changing the mass of the black hole?
H right plus H.
Yeah. Is that right?
Yeah, I think so. Yeah.
Okay, so the classical phase space, is this right? That if I wanted to look at the full classical phase space about this black hole background, I would have all the gravitons plus the change of the mass of the black hole. But that is the thing that gives you the full phase space.
Okay.
Now, if I look at the symplectic form of this phase space, what is this change in mass of black hole? Does it have a symplectic partner? That is this large diffeomorphism.
The time shift.
This time shift. I see. So there's this one extra mode, and this one extra thing, and this is like an X and a P.
Yeah. It's like
And
an excellent.
this is the quantization that you're doing.
Yeah. And one more thing I just wanted to add from yesterday's discussion is that you're asking about the boundary, right? What happens in the boundary? I checked Witten's paper again. He does a proper cross product in the boundary. He introduces a new degree of freedom, which is conjugate to the boundary Hamiltonian. So it's explicitly introducing a new degree of freedom in the boundary as well.
I see. So just to finish from the bulk. So if you were just doing a proper quantization of black hole spacetimes in the bulk, you would have this new degree of freedom. That would be somehow forced and you just semiclassical.
Yeah.
Now, so that part, okay, is great. Now, this cross product, is that forced in some way?
Yes, you have to implement the constraint. The operator algebra has to commute with the constraint. So that algebra has been dressed in the particular way, and only if you dress it in the cross product way will you achieve, that the fact that the algebra operator. So you have to impose the constraint that the generator of the killing isometry is HR minus HL. If you want to do that, you have to dress the algebra operator. And the way you have to dress it is exactly by the cross product.
Good. So then they're just semi-classically you're forced to do it.
Yeah, you're forced to. That's how I think.
Yeah, so that's very clear.
If you just don't do anything and you just say, I'll talk about gauge invariant operators, you come roughly to this at least.
Yeah, you will have to dress the operator to make it commute with the constraint, right? In a gauge space.
Then the great thing was that after that, the notion of entropy turned out to be just generalized.
Yeah.
That I thought was, that's kind of mind-blowing. Right?
Yeah. And it's been done more generally also. Any killing horizon, you can do the same construction for a spacetime with any killing horizon, and always the algebra entropy becomes the generalized modulo cost.
And is this entropy defined through little trace?
Yes, through little trace.
Sorry, I'm a bit confused the way you explain. Like the graviton mass will also go, like the gravitons will fall into black, right? So they are not getting.
But there is one other way you can change your spacetime geometry without exciting any gravitons. It's just change the mass of the black hole. Right? You've got a black hole solution which has mass n. So make it m plus delta. That is another classical solution. In addition, on top of that, you can excite gravitons. Now, the gravitons have their own Hilbert space, right? Their own phase space. So this guy looks like a mode that's left hanging. This is just one mode. It has a symplectic partner, and this must be this large difference. So now the quantization of the system forces you to introduce this new L2 degree.
Yes, yes.
So that's not some ad hoc thing. It's just there and not years.
And you have just introduced the right operator through the cross product, which leads to the algebra being type 2.
And then you say doing the quantization properly forces you to look at the dressed stuff.
Yeah.
Which sounds very plausible. So then this it's not really a conjecture. It just follows from quantizing semiclassical rapidly. That's very nice.
But from yesterday's discussion, I somehow got that this 1 degree of freedom is because you have lot of states and then you have.
That's the boundary interpretation. What is remarkable is that the bulk knows this. The bulk knows this just semi-classical. From the boundary, you can ask, what is this additional degree of freedom? And that is the phasing of this thermofield line. Right? Or the fact that you've got this sea of gluons and this is one parameter. But from the bulk, what is totally remarkable is that from the bulk, it's not some mysterious anything. It's just semi-classical context. If I got it right.
But in the context that people talk about is soft theorem and so on, where massless explanation. So there also, I mean, that soft mode is also kind of like, the mode.
You can consider soft modes also. They will not change the algebra. The time shift is the only thing which changes the algebra.
No,
Algebra type, sorry, I mean, you can always add more modes, but you can just add a relative rotation between the left and the right. You can do all those, but that will not change the algebra. This cross product is what changes that.
no, I meant that if you kind of do the similar type of, even in gauge theory, massless gauge theory,
That's the reason.
where you have a photon at infinity. And if you were to do this kind of construction where you would quantize that soft mode, would you be doing some sort of a cross product? Is there a way to think about it from a cross product point of view?
The cross product comes about when you want to implement a constraint. Okay, let me just.
I'm sorry, you must come. Will you give us the proof that this entropy is the generalized or that's for the reader?
I can give it on the board because
Okay.
these slides did not have it completely, but if everyone is interested.
Or maybe later you can tell me. I don't want to derail your talk.
Okay, so.
That's why I stop. One last thing, I just which is just to contrast this with global areas, where then the Hamiltonian is entirely determined by what's happening inside. Right? So in global areas, there's no other degree of freedom, it's just the inside stuff. So it's really crucial that there is this two-sided thing, so that you've got two edges. And that's what gives this new degree of freedom.
Yeah.
And that also from the field theory point of view makes sense because if you vacuum of the field theory is one state. You can't time translate it and get another state. Whereas the vacuum of a thermal state is not one state, so you can time translate it and get. So
you mean, but if I were doing ADM quantization in global ADS, yeah, I would also have to dress the graph.
you would dress the graph, but you wouldn't have a new L2 degree. It's not, there's no new part of your Hilbert space because that H is completely determined by constraints. Completely determined by what's happening inside. So what you have is a new degree of freedom with which you dress.
Would you have to refer to the asymptotically? No, maybe we just maybe what you're saying is that you fix the boundary time to be something. Is it like normally you take normalizable deformations?
I was saying the global constraint will just fix the boundary and the.
That's the dressing. The energy is fixed. Right? I mean, not just the energy, the stress tensor, some parts of it.
But if you have black holes inside, they would have
But if you have black holes, you have a second boundary. Or you have some other stuff, yeah. I need to put it away. Yeah.
Okay, so let me continue. Here's where we stopped yesterday. So the idea is you have this type 3 algebra in the black hole exterior. You do the cross product construction, you include the idiom degree of freedom, and you get a type 2 algebra, which has this trace. So we stopped at this. So now once you have this trace, what you can do is you can take the operator in the extended algebra and you can do this equation with the new modified trace. And you can find out, for example, what is rho phi. So corresponding to any state of this combined Hilbert space, you can figure out what is the density operator from this equation. And the entropy of the algebra for the state phi is just given by minus trace rho long for that density. So now I just want to mention here that these people have found that this algebra entropy is exactly the generalized entropy modulo constant. And let's see how they do it. So first what they do is they define a semiclassical string. Okay? it is a state which looks like this. This x here is the new degree of freedom. You can take it to be the left Hamiltonian or the conjugate pair. And g is a square integrable function. G is a function of x, it's a square integrable function. And you explicitly put in a small parameter epsilon and take states of this form. Yeah, just one.
X was the energy.
X was the new degree of freedom you have added, which you can think of as the Hamiltonian, the left Hamiltonian or the right Hamiltonian. Only one of them is.
Right, I guess I was confused why X goes from minus infinity to
Because this is a fluctuation, it's a fluctuation. So this is the state which they are working with. And now what you can
Sorry,
do, yeah,
what is the G is
G is a square integral function. Let me actually just write it here. So here's how we are going to
and five belongs to the trace to the space.
5 belongs to the big, this 5 belongs to the quantum field Hilbert state, and X belongs to that new degree of freedom that you have added.
So when you say quantum field, that's the graviton.
Yeah, the graviton and whatever quantum field you. Okay, so you have this relation, right? You just plug in this phi hat here, you plug in a hat here, and use the trace which we have defined for this new algebra. Remember that the trace uses the Hartle-Hawking state. Okay, this could be any state. So now you just plug everything in here and you do some operations with these modular operators. And then what you will get will be a rho phi. I don't have the details in my slide, so I thought I would just.
That's okay. And just, sorry,
Yeah.
you said trace uses the psi Hartle-Hawking. Yesterday you said that, right?
Yeah,
Uh,
so let me just write, do you want me to write the trace again?
you just once, if you can.
Yeah, so it is
And
dx
it's something to the
E to the
beta.
beta x. Psi a hat plus. And this goes from minus infinity. This is the trace. So this is the Hartle-Hawking state.
You take the Hartle-Hawking state, you compute A hat is some.
A hat is the
graviton.
Fourier decomposition of A in the new, with respect to the new degree of freedom.
And A was not. Yes.
So A was actually to start with your quantum field operator.
Now dress.
Yeah, now what you do is you define A hat is equal to from ds, A naught of S, e to the I, S, H, right? Or X or whatever you want to call it. And then you just, this is your A hat.
Okay.
Okay, so you just plug in this A hat here. And just plug in this trace, and what you do is you do A hat in this semi-classical state phi hat is equal to this. Okay, you figure out what is rho phi hat from here.
So you're trying to compute trace of the new density matrix. Is this right?
Yeah, you want, actually what you want is you want the density matrix corresponding to this phi.
And then you want to compute its entropy.
And then you want to compute it.
So you're going to compute that entropy by computing, how are you going to compute the entropy? You said-
So I'm going to use this relation. Okay, this is the relation, sorry, this chalk is not very clear, but this is the relation which is going to give me rho phi. Okay, so I put that phi here
For an arbitrary.
for an arbitrary A. For every A, it should be the same rho.
Yeah.
So what I'll do is I'll take that phi hat here, I'll put it in here. I'll take this A hat here, I'll put it in here.
Right.
Okay, and I'll just put in my trace here. So from this equation, I should be able to compute rho phi.
Okay.
Okay, and once I compute rho phi hat, then I will do Von-Neumann entropy of that particular density.
And this, the Hartle-Hawking state is for some fiducial. Like you are allowed to change.
Yeah, the Hartle-Hawking state is for the black hole that you started out with. It's a fiducial black hole, correct.
But phi hat, the general state will allow for.
Fluctuations,
Different
fluctuations.
masses, including masses.
Yeah, it will allow.
So expectation value is just normal expectation value of semi-classical quantum field theory. The right-hand
Yes,
side of this
Yes,
equation.
yes. So this phi hat is got both this part and this part, right?
Right.
So you have Fourier expanded your A hat.
So you look at it in Fock space,
This is your usual quantum field of it.
right? You look at it in Fock space and compute expectation value that way.
Yes, yes.
Okay. The more mysterious quantity is the left-hand side, which was at the slightly mysterious trace.
Yes, yes. This is a mysterious trace which explicitly involves the Hartle-Hawking state.
I see. So you're saying the expectation value by normal ways should agree with expectation value from the slightly mysterious trace.
Yes.
And thereby, by doing that, you compute that phi hat.
No, the expectation
No.
value from the normal trace does not work. This is a type
No,
2 algebra.
normal traces here. I mean,
Oh, yeah.
that's-
Okay, this is a relation which is obviously true for when you have a normal trace in a algebra in which the normal trace is well defined. We are importing this relation here.
I understand.
We are using the new trace here.
Yeah, so the right hand side is what human beings can compute,
Hmm.
and left hand side is what is your definition.
Is your-
And you're going to pull it out.
Yes.
Just 1 minute about the left
Yeah,
hand side,
sure.
which is what you wrote there
Hmm.
above
Is a trace.
is the trace of
A.
trace of A.
Yeah, trace of a hat
Any.
equals this.
And so.
Now I have here a trace of rho times a.
So having computed the right hand side through some reasonably standard procedure,
Yeah,
I am now going to try and reconstruct a row.
which solves this equation.
So
What is the S variable?
What is?
S.
Oh, this is just some Fourier decomposition. So you just take your a hat operator. A hat operator can be Fourier decomposed in terms of the usual quantum field operators times this.
So usual quantum.
So
field
this
operator
is
has
actually
S, right?
HR. This is actually.
No, I mean, this A naught of S,
Hmm.
what is that argument S?
That argument S is whatever is the conjugate to HR. HR is my new degree of freedom that I
That's the
have.
starting point, right? A naught of S.
Yes. A naught of S is
Some time
actually.
dependence, should I think of it as time dependent?
Yeah, you can think of it as that, because that's the conjugate variable. Yeah. Yeah. Think from minus infinity. And now you plug it in here and you get the rho. Okay. So now let me just write the expression for you get a rho phi and then you compute trace rho phi hat log rho phi hat. And this, I'll just give you the structure of this. This is given by the relative entropy between phi epsilon plus other things. And the relative entropy is between the state of the quantum fields for which you are interested in calculating this thing and the Hartle-Hopkin. And the Hartle-Hopkin state came here because of the trace. So this is the structure of the phenomenon entropy associated to any rho phi. It will be given in terms of relative entropy plus other things.
Other term is trace,
There are lots of other terms actually. And because this is you start with a computation in the extended algebra. So there are a lot of.
So here the relative entropy will be phi and psi, not phi hat.
Yeah, not phi happens. Okay, so that's what I have written here. And this is at this is at the leading order in epsilon. There will be corrections to this answer.
What was that like? This trace is equal to S relative. What was that statement? I'm sorry.
The trace rho phi log rho phi, which
Yes.
is
Which is
minus
not
of this is the
defined.
entropy
Yes.
associated with phi hat. Okay, and that is equal to minus this plus other.
That's a statement which comes out of the.
Yeah, out of
construction
the calculation, out of
construction.
calculating rho phi the way I did.
But in that formula for S relative phi psi. What
This
notion
is the
of S-
Hartle-Hopkin.
But that notion of S is.
Yeah, so I have
You have little trace, you have rho associated with phi hat, rho associated with HH.
yeah, so let's
and then you
let's
have
write
a
the
S.
let's write yeah, so let's write the relative entropy. Usually it is given by
Right.
trace rho phi log. Now let me just see if I got my so it's either this or with a negative sign.
There are two terms, right?
Yeah, there are two terms. One is trace rho phi log rho phi, the other will be trace rho phi log rho psi. And the difference between those two is the relative.
Maybe. No, all I wanted to ask was, I vaguely have understood how to compute little trace rho phi log rho phi, once you identify, say what rho phi is. And then, what is rho psi? How do you? it's
Yeah,
something
so
very
rho psi
straightforward.
and Hartle-Hopkin, rho psi.
And it's something very straightforward in your construction.
Yeah, the same way I did for rho phi, I would do rho psi.
But this is this fiducial.
Yeah, actually, I am cheating a bit here because whatever formula I'm using for the relative entropy is not this. Okay, this it is actually so usually relative entropy is not with this new trace, it's with the Hilbert space trace.
Right,
This is what it is.
But I thought,
Yeah, but there is a generalization of the relative entropy for type 3 algebra.
we're
Yeah.
using a little trace.
So we are using something called relative modular offset. So this is in Tomita-Takasaki theory, there is a generalization of the relative entropy. Because here you require the Hilbert space trace to give you something finite. But there is a generalization even for type 3 algebras, which comes from this Tomita-Takasaki.
That's
And that's what you get in the calculation. When you directly do this, that's what you get in the calculation.
I just trying to make sure I understand. When that's what you get in the calculation, if I compute with little traces, I get the
Yeah, so if I compute this object, after computing my rho phi hat, if I compute this object, then the relative entropy that I get, because I'm doing this, so the relative entropy that I get is the relative entropy for the type 3 algebra, which is because these don't come with hats.
Sorry for that. So the calculation you do is little trace rho phi hat log rho phi hat.
No, the relative entropy is the Hilbert space trace.
But that's a ill-defined number.
That's ill-defined. That's why I'm not using that. That's why I said I'm cheating a bit. I'm just writing the general formula for relative entropy here. But what actually is being used in the calculation is the generalization for a type 3 algebra.
So there's some generalization.
There is some
I don't have a problem with that.
Yeah.
But what is the statement? What equals what? So there are S
Yeah, so
relative now
this algebra entropy equals this
that. That's
relative
the
entropy.
statement. Okay,
Yes,
fine.
plus other things.
Okay, now I get it.
Left hand side is some stuff you do, your grand construction.
Yeah.
Right hand side, I can think of a semiclassical.
Yeah.
No, S relative and also some Tomita terms.
But that's a fancy way of saying semiclassical. Right, just with the field theory.
You are.
And the other terms are.
Is that what it is?
Yeah, other terms I'm just going to tell what.
Because relative to divergences will get.
Oh, that's what you mean.
I think so. I think you just do it to the cutoff, you do subtract it to the cutoff you get.
Somehow there are other terms, right? Like.
Yeah.
Yeah, there are other terms are
But there should be other terms, right? Shouldn't there be a change in area?
Yeah, exactly.
Yeah, there will be all those terms.
Yeah.
Okay.
I see.
So now the next step is actually something which was shown by Wald in his original proof, is that the relative
So,
entropy.
Is this something that you wanted? This is your final result, or you're going to tell us more about what you get here on the right hand?
Yeah, I'm going to
Yeah,
tell you
yeah.
more about the relative.
Okay.
Okay. So the relative entropy turns out to be the generalized entropy at the cut V, when the cut V of the black hole horizon is taken to infinity, minus the generalized entropy at the bifurcation surface B. This is what relative entropy turns out. So that's how the generalized entropy comes into the answer for the algebra entropy. So if you want, I can tell you more about.
S to infinity, you take the killing horizon all the way up to infinity.
Yes, you take the cut at infinity. So you just take your, you just start with your black hole.
Right.
And this is an arbitrary cut. Then in the, in the limit where this cut is taken to infinity, so that's like your final,
I understand.
generalized entropy.
Yeah, okay.
And we know from quantum field theory that the relative entropy is always positive. So you know that the generalized entropy at the cut at infinity is much bigger than the generalized entropy at the cut at the bifurcation. So S gen infinity is greater than or equal to S gen. Okay. Now I can.
Just one, so I understand when Aaron Wald showed this relation, this S rel phi / psi is computed by taking a black hole. Two situations corresponding to phi and psi both involve black holes of some mass and stuff outside.
Now you take the Raychaudhuri equation.
Is that what he did, or did he just compute?
No, we took the Raychaudhuri equation, and then he.
No, I'm not saying for the proof. I'm just saying for the definition of S rel phi / psi.
Oh, that comes from the Tomita.
So that's what this is that relation.
So actually what Wald did not bother to go to Tomita-Takasaki theory.
Right, so what
He just used the definition of a.
So he
Of the
looked at
relative
generalized, he looked at generalized entropy for phi. I mean, he looked at, one of these terms is not an obvious term because it's trace rho of phi and log of rho of psi.
Yes.
One of those terms,
Yes,
right?
one of those
And
terms.
I don't know how to compute that semi-classically in a straightforward way?
So that would just be phi log rho psi phi, right? If I had a way of getting log rho psi, then I would do this.
That's fine. There's one term in relative entropy which involves
Which is this term.
both the rows, right?
Yeah, this is,
Okay.
there's one term involving rho phi and other one involving.
Okay, and just, I'm so sorry, but just if I were a simple-minded person and you told me to compute trace row log row, okay, I could do that. I would take all the quantum fields, I'd cut them off, and I would maybe do a generalized entropy. Okay, but if you ask me to compute trace of rho phi log rho psi, you know, it's not something I do, but maybe the claims do it in some way.
Because psi is a special state.
So
Yeah,
then-
psi is a special, that's exactly right.
So then we can do this.
Yeah, so you want me to show you?
No, I'll ask you later. I just, these are things I don't know as well as I.
The point is that log of, because psi is the Laplace state, it's modular, algebra, and the local object. So you can actually write it. It's just the, essentially the.
Both, exactly.
So log, you know what log of rho psi is. So that's.
So you write it in terms of some stress tense.
Yes, exactly.
Okay.
Both,
I see.
just
So
the,
that's what he showed.
And then that enters the right order.
yeah, exactly.
Is this relative entropy we expect from a parallel?
So this is actually, this relative entropy in Wald's proof, he just used the standard formula for a relative entropy. And I told you why psi comes in there, right? It comes from the trace.
No, but is this something we expect, like the entropy or something should be like some relative entropy?
I don't know if that's an intuitive way to argue that this relative entropy should be S gen infinity minus S gen.
But will you show that this S relative is something area over 4G Newton or something?
Yeah, because it's already S gen infinity minus S gen B, and S gen has the area in it, right? So it's area infinity by 4G minus area B by 4G plus other things. So it already comes from there.
And those other terms are the other terms that you got in your.
Yeah, so let me tell you what the other terms are going to do. Those other terms will precisely cancel out S gen infinity. Okay, so you will be just left with S gen B. So the algebra entropy just turns out to be the generalized entropy at the bifurcation surface plus a constant. Okay, then what they did was this algebra entropy was proved, written proof. Yeah.
The S gen infinity go inside the C.
Exactly. You put the S gen infinity in the
So
C.
you're the infinity inside S gen
Yes,
infinity
yes,
is taken.
yes. And this is under the assumption that in any state of the quantum field, if you
Oh.
wait until infinity, it becomes the Hartley law. So that makes this constant now state independent. Okay. Now,
Infinity means what? Sorry, what is?
S gen infinity means,
What does infinity? What is?
yeah, infinity is you just take a cut V and let the cut tend to infinity.
Oh,
The
no,
cut
it's
is
in
back
time.
backwards, yeah.
That-
So the
that-
cut is the
argument is
backwards.
time.
Yeah, here's where you're computing generalized entropy in general, right? At an arbitrary
So the
cut.
argument is time.
I find that.
And the state phi can be specified on some Cauchy slice, right?
Yeah,
Presumably-
state phi
On some
can.
Cauchy slice, but
Yeah.
then this is the relation.
Yeah, so the Cauchy slice will cut the horizon somewhere.
Isn't that-
Yeah, so the Cauchy slice will cut the horizon like this.
So you want to.
So at later and later cuts, you have.
So in that formula, I'm supposed to take a Cauchy slice which ends at infinity or on the horizon. Is that?
It
is that
ends on the horizon, and it can go here like this, it doesn't matter, but the slices look like this.
The slices look like that, but just
So
sorry.
now you take the cut to infinity, then you get S
You
gen.
get but the state phi presumably is defined where, because if stuff is falling into the black hole,
Yeah,
as you change your cut, you will have different amounts of matter outside.
yeah, that's right. So phi has that information in it, and when the cut is taken to infinity, then phi becomes psi.
I become psi, but
Psi part of it.
uh,
Because you assume everything would have fallen into the
in
horizon.
that formula,
Hmm.
when it has S rel phi psi, that phi is defined at some initial instant, right?
Yeah, that phi is defined actually in this calculation, it's S gen infinity minus S gen B, right? So you start with S gen B, and then your phi becomes psi at infinity.
Is independent B.
Yeah,
Actually, SGN, what was SGN B? Black hole.
bifurcations.
Black. So that's what I was
Yeah,
thinking.
yeah,
So you
sure.
define your slice
Yeah,
perhaps as going, as a space like Cauchy
yeah,
slice
so
going
this
through
is
here.
Sgen at B.
And you define your state phi here.
Yeah, yeah.
And then you compute the relative and that equals, right?
Yeah.
Okay, now I understand. Thank you.
Now, the thing is, this algebra entropy was proven by Witten to be monotonic in this following way. Okay, so suppose you have a algebra A and you have a subalgebra of that algebra A, then what happens is that for any state phi, S of phi hat, yes, so S, let me just write it here. So suppose I have an operator in B and I take the trace of the operator in B using algebra A, or I take the trace of operator B using the algebra B. Okay, if these two traces are the same, then the algebra entropy is 1. So that's something which Witten showed. And then they want to use the monotonicity of this algebra entropy to show that generalized entropy increases. But the problem is you only got the generalized entropy at the bifurcation space. Okay? And also, what happens is that because you now have the Hamiltonian, you have included the Hamiltonian as part of your algebra. If you, for example, look at ADS-CFT, the Hamiltonian will take you out of any wedge that you might draw here. So, for example, if I want to prove that the algebra entropy, if I want to prove that the generalized entropy at this arbitrary cut increases, okay, as the cut goes to later and later, you will not be able to do that because this algebra of operators here, or the ones dual to this in the CFT, will not actually be a subalgebra of the full algebra because it involves a Hamiltonian which will take it out of the algebra. Okay, so you don't get a subalgebra of an algebra for which you can use this monotonicity of the algebra. So they have a very clever argument where they say that let us assume that at some early times there is some matter that falls across the horizon. At late times, there is again some matter falling across the horizon, but there is no matter falling across at these intermediate times. And in that case, they are able to show that there is a GFR in the sense that the generalized entropy increases between early and late.
Let me ask you the following, and then we can talk about it later. In 2D, you can do the following thing. You can actually do the down-to-earth calculation of generalized entropy. You need to introduce a cutoff, but you say, I'm going to keep the cutoff in physical units fixed, right? And then you can prove it's generalized second. Just generalize right away. So, I mean, here, what they're trying to do is get rid of that cutoff dependence, right? By defining something.
Yeah.
But, I mean, at root, is this what they're doing? That, because physically, you say, I'm going to keep the cutoff, in physical distance as measured near the horizon in some freely falling flame to be fixed, right? And then you can prove a second one. Now, here, maybe by taking a relative entropy, they get rid of that contribution.
Yeah.
But the
no, but even then, there is
the issue.
the issue. So the issue.
Really, sorry, just to say, just as you prove the second law with as much generality, that you need the notion of an event horizon, but then you follow it in the past. And you can prove that monotonically. Yeah, okay, go ahead, sorry.
Yeah, so what Wald did was he unpackaged the relative entropy into its pieces. Okay? Each piece is divergent. And he just said that if there is a renormalization scheme that renders these pieces finite, then I will use the monotonicity of the relative entropy and I will prove the J's. So what these people tried to do was to get such a renormalization scheme, but they still did not get this local J's, where the entropy increases for arbitrary groups. They didn't get that. And now I'm just going to show you here how you can get
which
that.
argument requires that nothing happens in the middle?
The argument which they gave, which is that the generalized entropy increases from early times to late times. So there you need a separation like this. In their proof, you need the separation.
Okay.
You don't have d S gen by dv is greater than entropy. You don't have this result. Now you need this result.
Where do they use this argument?
They use this and the monotonicity of the algebra entropy to prove that generalized entropy increases between late and early.
Which part of their argument requires that there be no matter falling in?
Yeah, so what they do basically, see, the thing is they have only got that the algebra entropies is equal to S gen at a bifurcation point.
Yeah, okay.
But you want to prove this for any cut, right? So what they do is that they take early time operators and late time operators, and they identify the three states. Okay, one state is where both sets of operators have not fallen across the lines. Then the second state is where the first part has fallen and the second part is still there. And the third state is where all of them have fallen across the lines. They compare these three states. Okay, and they use some clever arguments to show that you can just work with the generalized entropy at the bifurcation.
Roughly speaking, if you wait long enough after something's fallen, it settles down. So that's like a new bifurcation.
Yeah, exactly.
No, but is it this monotonicity? You mentioned that there's monotonicity of relative entropy that we use.
No, not here, not here.
One algebra which is not
Monotonicity, they use the monotonicity of the algebra entropy, which they prove.
Is it right, Suneeta, that the main accomplishment is giving, it seems to me that the main accomplishment is giving a completely Hilbert space description of the generalized entropy, including the area.
Including the area.
That had never been done before. Is that right?
That's true.
Okay, the rest of it, the right hand side of everything is old. It's just semiclassics. This is more than 10 years, right? Whereas new is that the right hand side had a part that was Hilbert space and a part that was not. Because the area was not Hilbert space.
Exactly.
It was just added.
Now you've
Now,
added it as
both of
part.
them together come from a single Hilbert space.
Yeah.
That is the main accomplishment.
Yeah.
This is right.
Yeah. Okay, so now what I want to do is I want to get a local GSL. So for this, we needed a result which came soon after, which was by these people. What they did was to completely generalize, Witten and collaborators' construction to associate an algebra entropy to any subregion of spacetime, which is domain of dependence of some partial Cauchy slice. So you just take some partial Cauchy slice, you take its domain of
I
dependence.
would have waited, but I don't see such a great distinction between having a black hole. I mean, if you take global ADS and you have a black hole that forms and collapse, you have one boundary, but you have a horizon, right? And you have a generalized second law which one can derive from old-fashioned ways. So,
Yes,
I
you
mean, I
can,
can just apply these arguments there, right?
you can
And
apply that and
wouldn't
translate
you
that.
need to augment your Hilbert space according to them by the extra degree of freedom corresponding to mass or not?
So you will have to augment that, but you can prove this GSL for one-sided black holes. It has been.
No, you better be able to,
Yeah,
right? Because
yeah.
that's a physical situation.
Yeah.
But then you don't, I mean, so then are you not augmenting? I mean, this is why.
But then you have to invoke some other something, right? Some other place where the thing can rest. These degrees of freedom in the bulk, if they all rest to the boundary, then you don't need some other. You have to have some other place.
Yeah, so what you do basically, you
address, I'm not sorry, please excuse me. I thought even in that case, with one boundary and a black hole which forms from collapse.
No, you don't have one boundary. Okay, the trick is this, that what you do, you take any one-sided black hole can be extended.
No, I don't want to do it.
Okay. If you want to do it, if you don't want to do it, then you can't.
collapse.
If you don't want to do it, then
But
this
this
stuff.
is only, there's a.
No, this is, so let me just say, if you have a black hole, you have a two-sided black hole, then of course you can do this construction. For the one-sided black hole, you should still extend it. You can always extend the black hole such that you keep this portion, right? This portion.
But I mean, I can draw a
The
complete.
past
nice-
horizon.
I can draw a complete nice Cauchy slice when you form from collapse. And I can, define a generalized second law and in some cases even prove it using old-fashioned methods, right? These arguments don't apply to.
No, you have to basically extend the black hole form from collapse such that it now includes the past horizon, and then you can.
There's no past horizon in the physical.
I suspect you'll do a Papadodona style. You more or less construct the second side out of very complicated operators and then do that. That's roughly what I suspect.
But why can't we think of this solution?
That's sort of crazy because there is an old-fashioned generalized second law. If I just keep the cutoff fixed in invariant units.
But that's the right hand side. The semi-classics, they're not doing anything. The new thing is to produce a Hilbert space in which everything, including the area term, comes out, and then prove entirely using that Hilbert space homology everything.
But
I don't think there's anything new on the text. That's my
the way you were saying was that this came from the modulus, right? It's modulus of the solution. That you have this mass which you can change, which becomes part of the phase space. So even for this solution, there will be some direction in the phase space where you can just change the solution, right? By changing the mass of the collapsed black hole. So you could still quantize that degree of freedom, giving you this extra.
I mean, I think Shiraz's original point was that if you just when you just collapse, then you don't have anything extra. You just have one boundary, it's a standard thing, and you have.
No, I mean, just in terms of phase space, why can't you have this? Why can't you have this?
Yeah, well, why don't you have the extra degree of freedom? I thought
that is what you would
the
add to that and then quantize.
I know the answer being given is that if you try to think of those solutions, then you have to think of them as the extended set.
Yeah. Extended, or you don't need to get the second.
With the two sides, with the two asymptotic.
But that is then a matter of interpretation. But just the fact that you have that part in the phase space should address this issue.
You just need the full Cauchy lines. So you either take this and this.
There is a physical question. I have one boundary, one connected boundary in CFT, and I want to just quantize the system. I want to understand generalized second, right? I mean, this is a physically well-defined question, right?
There is a modulus in that case, right? For instance, you have these states that end with the world trains behind the rest, then we can ask for the length of the wormhole up to the end. There is a mode there.
Yeah, what we going to end up? I don't know. I mean, normally when we do ADS CFT, I don't know what we don't bother about dressing. You know, you have a lump of gravitons. I map it to some state in the boundary theory which has an expectation value of stress in it. I'm not supposed to introduce a new thing, right? In the as per the usual rules of it. Otherwise, we are changing rules of ADS. Yeah. Okay. So I think one way or another, what we do is we sort of gauge fix. We say, I'm not going to do very large diffeomorphisms on the boundary because I know once and for all what the time of the boundary gauge theory is. And then, with that fixed, I talk about a lump in bulk and something like this, right? Okay, I mean, it's a little unsatisfying to me if you can't, if all of this, I mean, to the extent, I feel what this is doing is getting rid of infinities and intermediate steps of entropy calculation. Then you should be able to do it there also, right? I mean, or you can't do it on this.
The right-hand side even surely, the semiclassics is no problem.
It's fine. Getting the area.
It's the left-hand side, which I also agree that you should be able to do.
That is right-hand side is area plus entanglement entropy across horizon.
That you guys did
no,
I mean, that's cool.
Okay, and subtracted between two states.
Yeah.
Okay, left-hand side is what? In algebra interpretation.
Find the Hilbert space such that this entanglement entropy, this is an entropy in that Hilbert space, including the area. That's the thing.
You have to include the Hilbert space of fluctuation of the area.
Of the area. And if you had a single boundary, you don't have that.
Why don't you have it?
No, that's what I'm asking. I mean,
This modulus is that right, the thing that you fix, you don't want to fix that.
No, but I mean,
Want to allow-
if you don't want to allow like into the world brains, you need the second degree of freedom. That's exactly.
But let's look at it from the CFT point of view. From the CFT point of view, you have a high energy state. As long as it's not an energy eigenstate, it's some random superposition of energy eigenstate. You have this degree of freedom, right? Because you can phase it.
Yeah.
So you have that.
what is the degree of freedom? Sorry.
So the CFT interpretation of this degree of freedom, at least in the thermopile level setting, was that you evolve from one side with the Hamiltonian. What that does is that it phases.
It phases the, but relative phases, right?
Exactly.
So that's something not true.
So it's doing something non-trivial. And from the power point of view, that corresponds to increasing the length of the bond. That's how I like to think about it. There will be others. Now, if you have a single-sided state, again a high energy eigenstates, you can still phase it. And again, from the
the phasing with a single boundary is just evolving with time.
correct.
I mean, that, okay, we don't need an extra degree of freedom, right? I mean, the CFT Hamiltonian does
but
that.
that evolution with time is cannot be mimicked by adding trace operators.
Yes.
So it's a new thing apart from the graph function. That's the key.
I mean, is this the point that the Hamiltonian is not a well-defined operator in the larger limit and needs to be included?
Yes.
I mean, there was some story like this about Witten, right?
Yeah.
Maybe that's the
Yeah, yeah,
statement.
yeah.
Okay, so we understand it in a single boundary case by saying that I don't know what it is, in some normalization, you take the Hamiltonian divided by n square or something,
Yeah,
then you keep it.
exactly.
Otherwise you won't keep it. That's the statement? Oh, okay, so this is how it all ties in. And then Shiraz, maybe there is an extra operator you have to
I think so, but I feel that the bulk story is cleanest in the blue side.
It's cleanest, but I'm just saying it would be unsatisfactory.
Yeah, but what the bulk, you see, what I really like about it is that you don't have to invent any rules. In the two-sided case, you just do normal semiclassical quantization.
Correct. It just gives you this.
And it will come out. Now, in the one-sided case, you will have to say some words or invent some rules. I think.
Yeah, but I'm not sure, you know. I mean, I'm not sure.
You have to impose a constraint that the bulk, stress energy and the energy of the bulk should be equal to the boundary between radian and the same constraint, right? That you were imposing and for the two-sided case.
No, but that was the second thing, right? That you could have some of the energy going here and some of the energy going there. You need some envelope of that. Then you need something to dress it, alternate dressing.
Okay, actually, let me just,
You must go on.
no, let me just talk about this construction. This is what was used for a one-sided graph. So,
Okay, that's why I
Yeah.
thought I'd ask the
yeah,
question.
so let's just talk about this. This is the entropy associated to any subregion. Right?
Yeah.
This is a new proposal by this.
Okay.
So what they do is the following. They impose a constraint. And the constraint is the Hamiltonian, which generates the flow of a very particular class of diffeomorphisms on a Cauchy slice. Okay? And let me just show you what the diffeomorphisms look like. So imagine that you have a region, diamond-shaped region here for which you want the entropy, for which you want to do all this construction. So you take a vector field which preserves the diamond-shaped region, and in the the causal complement of that diamond region, it runs in the opposite direction. Okay, it preserves all these boundaries. The flow of the vector field is such that it preserves all these boundaries. But the thing is, it's not a killing vector field. Your spacetime need not have any killing symmetry. You just consider this vector.
This is just some random vector.
This is some random, you can choose whatever vector field you want which satisfies these.
So you just look at some spatial subpart of the Cauchy slice and construct the causal.
Exactly.
Right.
So this causal diamond, let's say the region for which I want to do all this construction.
Yes.
Okay. So the vector field behaves like this. It preserves the causal diamond. It preserves its causal complement and runs the opposite way in the causal complement. You know that this mimics what the killing field does for the Schwarzschild black hole because it runs in the opposite direction in the left as compared to the right. But this is not a killing field. So this is just any vector. Now this vector field will be generated by some, by some Hamiltonian. Okay? So what you do is you impose as a constraint this Hamiltonian. Now you should actually do this for all types of diffeomorphisms, but what they do is they just consider this class of diffeomorphisms. And then they impose the generator of this flow on a Cauchy slice as a constraint. Now these diffeomorphisms,
Just to say, for the single-sided case, I would say this is exactly the Hamiltonian as seen in the outside.
Yeah.
As
So
per
this is how you use to get the single-sided.
But then are they saying in the end that you have to add this extra degree of freedom?
Yes, you have to. Let me just tell you what is that degree.
I think one way or another for the single side, this extra Hamilton n square story or something, which, okay, go ahead.
Yes. So this constraint, which is to implement this, generator of this flow as a constraint, this cannot be imposed without adding one more degree of freedom. And that degree of freedom which they add is an observer degree of freedom. Okay, an observer is some additional clock or some degree of freedom associated with that particular diamond-shaped region, and it has an energy Q greater than or equal to 0. Okay, and the constraint which is imposed is you add an observer in the diamond-shaped region, you add an observer in the complement of that's Q prime. And then because the killing field the vector field runs in opposite directions along the slice, you have a relative sign between Q and Q prime. And what you want to impose is the bulk part of H plus Q minus Q prime as a constraint.
This observer is like the second boundary.
Yeah, so the observer degree of freedom has to be added by hand. So you would think of this as an entropy associated to that observer.
Where does the observer live?
So the observer lives on the Cauchy slice of that diamond.
Okay, particularly.
Can you just show?
You can make a word line if you want. So if you want, you can take this diamond shaped region. You can take a word line like this, okay, such that this diamond shaped region is the intersection of this past with this future. Okay, you can think of the word line of this as an observer.
It's a little like your undercover.
Yes.
So in ADS-CFT, of course, Subrat has a paper where he's trying to understand what this observer is.
So this is Q, and what is Q prime?
Q prime is another observer in the causal complement. Yeah.
But I thought from the two-sided black hole, the lesson that I thought was that you have this.
ADM Hamiltonian.
Yeah.
That's for the two-sided black
That gives
hole.
rise the area
Yeah.
piece for the
Yeah.
horizon, right?
Yeah.
So there is no horizon here.
There's no horizon here. This is an arbitrary domain of dependence in an arbitrary space. Okay, and their proposal is basically they want to implement that flow as a constraint. Now the thing is, if you want to impose the constraint again, you have to dress your algebra operators. So your algebra is now the algebra associated with that diamond. You dress your algebra operators with this Hamiltonian H. You introduce the new degree of freedom Q, and you take the double commutant of this algebra so that it becomes a ornament. So this is a cross product algebra, but it's not yet cross product algebra by the modular Hamiltonian.
Can you explain the first line again? What is the reason behind it?
Which first line? This first line.
Yeah.
Yeah, the point is if you try to impose this as a constraint on the states, right, you will not find any states satisfy that.
Well, impose this as a constraint. What is
Yeah. So there are two things, right? One, you have to impose the constraint on the Hilbert space.
constraint? What is the constraint?
So the constraint is that the flow of the bulk part of the flow of that diffeomorphism. So in gravity, you always impose a constraint, right? So you do an ADM decomposition, let's say of your spacetime. Okay, so you have a ADM Hamiltonian. The bulk part of the ADM Hamiltonian is the constraint, right? You may have a boundary part if the spacetime is non-compact, but then the bulk part of the ADM Hamiltonian is a constraint. Yeah.
I see.
Now what you're doing is you're implementing the flow of a particular diffeomorphism as a constraint. And I just showed you what. Yes. It becomes the usual d by dt at the boundary.
So then that minus d by dt is.
Is the bulk part, the bulk part.
That's why there is Q in time terms. It's not actually time.
Oh, I see. So that it implements what it should implement.
Yeah, so here is the flow of the vector. This is what the H is doing. So it behaves, in particular, I forgot to say that it behaves like a boost on the boundary.
Right.
Okay. So now what you do, in order to implement this constraint, you have to dress your algebra, and then you make it into this cross product algebra. Now, if this H were a modular Hamiltonian, which is what we defined yesterday, then this cross product algebra would now become type. Okay. So these people assumed in their paper that this H, which is the generator of some diffeomorphism like this, is a modular Hamiltonian for some state. Okay, it would not be the modular Hamiltonian for the vacuum, that you can show, but they just said maybe it's a modular Hamiltonian for some state. Now, if you do that, of course, then the whole story just follows that you have a type 2 algebra, you can define its entropy, so on, so forth, and then you can show that the entropy is a generalized modulo of.
Sorry, so if I could say this way, that you've got some stuff. Either it's energy, causal or energy has to go to the boundary, or it goes inside. If it goes inside, it has to end somewhere.
Yeah.
Otherwise, it violates diffeomorphism. So that's why you have to introduce the new.
Yeah.
Is this what?
Okay. So
That picture, what is outside, what is inside? That's I want picture.
One side is outside, one side is inside.
no, the diamond is
Diamond
the region you are interested in, and the causal complement is the pollution. Yeah.
I thought to the right of the diamond was outside, to the left of the diamond was outside.
Both outdoors and outside. I mean, the left, right.
But is it one side inside the horizon roughly? Yeah.
No, there's no horizon. There's no horizon. This is just any arbitrary space-time. This is any arbitrary causal time.
But you're applying this, let's say, just to global ADS?
You could apply this anywhere, but then you need this.
But in global ADS, we should not have to introduce some new degree of freedom. I thought only horizons were.
This is a construction, you can think of this as giving you some entropy associated with that observer. Entropy as measured by that observer.
For an arbitrary surface, even in geometry.
Yeah.
Suppose you just.
You just make a system.
Yeah.
Define it.
And but why is it stopping here? Why is the diamond like finite?
The finite region.
You just
So
take
you
it,
just have this finite region and then you want to understand what is the.
and the region is defined by the observer. Okay, the observer could be a world line in that region. And then you're trying to measure the entropy associated with that. This is just a useful construct which we are going to use in a case where all their assumptions are actually.
Actually, let me just ask you something. You need, can I just do it? Can I just do it for the causal diamond by itself? Do I need reference to your other observer
Yes,
outside?
you need,
You do.
you need, in order to implement the constraint.
But I mean, there's a way you can just implement the constraint in the causal diamond.
So what the vector field that you have,
Maybe not.
the vector field that you have is having a non-trivial action here also, right? It's not a compactly supported vector.
But usually the time reparameterization constraint is local in space. And so if I integrate it against vector fields which only have support in this region.
Yeah, but the vector field does not have support only in this region, right? What I'm trying to say is it has a non-trivial action.
All I wanted to ask was if what I'm trying to do is associate some notion of gauge invariant operators in the causal diamond, and yes, I need to dress it to something. I introduce the observer in the causal diamond, that's not enough.
For
I
this
need the
vector
global.
field, it's not.
But I could just say the vector field is zero outside.
Yeah, you
and
can do
then
that, you can do that, you can do that, certainly.
I mean,
So the reason why we are taking this particular construction is because it directly applies to the block.
Sorry, Suneeta, please one more time. If I were to just want to semi-classically quantize global ADS without horizons, I'll have no time. So just tell me again, what are you trying to do?
What these people are trying to do, they are trying to associate this whole algebra entropy construction to an arbitrary region in an arbitrary spacetime with no symmetries. Then you need these observers. Okay, you need these observers to preserve this diamond and to preserve the causal complement. To define the diamond and the causal complement.
Later on, but I mean, take the case, I also want to take global ADS, and I want to talk about gauge invariant operators in the bulk, which will commute with the constraints. I need to dress them in some way, right? Maybe we need this extra operator for that. You may say, come on, we've been doing ADS CFT forever, but maybe you need the extra operator that generates the phase on the bulk.
The fun thing is that we want.
I don't know.
I don't think so.
No, you're probably right, but I mean, I have a kind of disconnect in that. You're probably
Yeah, I'm
right.
thinking about this, that you're trying to define this algebra of operators for the primary case.
Yeah.
And if you try to gravitationally dress operators in that region with the asymptotic boundary, they will not commute with outside. You want to define an algebra for the diamond and a commutant algebra, which is like outside, right? Outside it. You need an algebra and it's commutant. Now, suppose you decide to dress all the operators to the asymptotic boundary, then they will just not commute with them.
Yeah.
They will be part of the algebra.
Yeah.
You're not actually defining a sub-algebra.
You have to dress them to the
So you
observer.
need some way to dress them without such that they commute with everything.
Yeah.
So the one way to do that is to introduce this observer and you dress them.
Yeah.
Then you can find.
I completely agree, and therefore introducing the observer inside is crucial, right? I was just saying, I was just saying that I guess maybe your point is that you want, if you don't define in a precise way the subalgebra, then you haven't done anything. So the role of the Q prime is just to make sure in a.
No, the Q prime is also because the vector field is non-trivial.
I know that's what you said, but then if
You
that
can,
is.
yeah, so you can do for some vector field which is only inside the causal diamond. But that's not what we need for the proof of the GST. We need this construct.
Otherwise, somehow it doesn't. Although you could then dress and define local operators inside, maybe you can't in precise sense say it's a subalgebra till you have the Q prime outside and you dress with that. Perhaps that's why you need both.
But I'm just trying to understand, sorry, what are we trying to do? We've got some region in space-time. We should not in gravity be able to associate
Entropy to the region,
arbitrary
to the
right?
region,
Yeah.
but it's an entropy as measured by an observer, let's say, who's having a world line in that region.
Okay, so now this is a question related to it.
Yeah, related to an observer.
No, but apparently it has some beautiful geometrical answer.
Hmm.
It's the generalized entropy of that region. This is the kind of miraculous thing, really. It seems
Where
also
the
very
area
interesting.
by 4G is in that,
In that
there's
region,
2
and
points.
so two guys in that region will get the same entropy. And it doesn't matter which the observer is,
Yeah.
etc., etc. So eventually it's some very general.
Yeah.
Because it depends only on the, so
It all depends only on that region.
the observer lives forever.
The observer could live forever, but you are looking at the observer between sometimes T1 and T2, which
T1.
define for you the region.
I mean, through the region, lives forever through that.
Through the region, but this region is finite time.
It could be infinite also. It could be
Could be
asymptotic by Jones.
In a global area, so it was infinite. Okay, does he come from the just give me an example in global area? He goes from minus infinity to infinity. That's all of global. Right?
Yeah, that is also an observer. You can have an observer doing that.
Observer.
You can even take time band. You can take time
You want the observer to live for a finite amount of time.
Yeah.
It's from the CFT point of view, if you just have the vacuum state, then as you said, the Hamiltonian is denied itself, right?
Yeah. There's no extra thing.
So this observer is playing the role of some exciting.
Okay.
So then now you have some.
Yeah, so you've got some star, very complicated neutron star, you know, this, you operate
Exactly,
the
exactly.
degrees of freedom there.
Exactly. You can take a star.
Okay.
Playing the same.
But of course, not all regions would be obtainable in this way, right? As a finite life observer, just geometrically.
All domains of dependence of partial Cauchy slices.
Be obtainable like this.
Because you can think of an observer that's going like this, okay? This is the future light cone and this is the past light cone at these 2 times. Then the diamond region is that.
It depends only on the points, the top and the bottom.
Yeah, exactly.
Yeah, star region.
That would be amazing.
If you have a star region,
Yeah, it's like a company.
then that's probably difficult for this to be.
Which region?
If you have a star-shaped region on the Cauchy slice, let's say.
Is the star-shaped region the domain of dependence of some Cauchy slice?
No, Cauchy slice spatial region is star-shaped. So
Spatial.
then you make some this thing.
Mhm.
But then if you start having observer, it will include the full thing. So you just cannot put it only in that region. But
You know, before you ask what is the entropy of a black hole, beautiful, nice interpretation also of the quantum field theory. This sounds like very easy question.
Yeah, wait. It's going to apply, it's going to get applied to the GSL, and
Okay,
then
fine.
that's the only utility I see for it now.
Okay.
Okay, so the problem is that they assume that
physical probably relevant, right?
Yeah. So
Yes.
Even this GSL context as Suneeta pointed out.
yes, it is what generalized.
second.
Okay.
In that context, as you pointed out, there is, you need to consider algebras which are not just related to the bifurcation.
See, you need to consider these kinds of algebras, right? You have this is your horizon, you have a cut like this is a region. You need to consider such regions. Because in Witten's proof, you only get the generalized entropy at the bifurcation surface. Now what I want to associate an entropy to these wedges.
Then you will have an observer in that wedge.
You will have an observer. You can think of that as a massive.
Wait,
tower.
what the question was how generalized second law, how the entropy increases with time.
Exactly. We want S gen to increase with time along this direction, and we need this construction to show that. So let me just show it to you.
Sorry, Suneeta, this observer that is there, I mean, this generalized entropy that you find using this. So there's some split of that as area term and.
Yeah, we're going to see that.
No, I mean, even just in this context of this arbitrary diamond shaped region.
Yeah, arbitrary diamond shaped region. We will get a generalized entropy in which this is the area at this point. Yeah. Okay, so what these people assumed was that their Hamiltonian which generates the flow is a modular Hamiltonian of some state. But modular Hamiltonians are really hard to compute, so it's not clear whether their conjecture is true or not. But there is one instance where the assumption is exactly true. Okay, these are when you have these specific wedges in the black hole spacetime that I showed. So if you look here, you have the A, which is the full right exterior, and you have the B, which is corresponding to a cut of the black hole horizon, which is later than the bifurcation surface. Okay, so these are the two kinds of wedges I will be interested in. Now, it turns out that the von Neumann algebra of operators on the smaller wedge has a relation with the larger wedge. It's what is called a half-sided modular inclusion. Okay, so I'm going to just explain to you what is the half-sided modular inclusion. So let me just define that. So what happens in a half-sided modular inclusion is that if you have a subalgebra B, okay, then if you take the modular operator corresponding to the region A, and you conjugate the operators in B with it, then it leaves you inside B for t greater than or equal to 0. Okay, so let me just show you the figure again. Yeah, so here you have this figure where I'm showing you what the modular flow does in the region A. Basically, it implements the flow of d by dt. Okay. So that modular flow, I'm interested in applying it to Schwarzschild. So let me just take d by dt, which implements this modular flow. And you can see that for t greater than 0, it takes a point in B and keeps it in B. Okay, so the modular flow acting on the field will do the same thing. It will take you to a field in B. Okay, so this is precisely what we call this half-sided modular. Okay, so yeah.
So what is A and B algebra? A and B is
So
there,
just the A is the full right exterior.
and all.
B is defined by this cut at least.
But then,
So the modular flow in A is basically just the flow of the Killing isometry. So you know how it acts, right? You know that for t greater than or equal to 0, it takes points in B further away only in B. It preserves the region B for t greater than.
I understand, but I want to define gauge invariant operators by tracing, right? Presumably, right?
Yeah, we'll do that
because
later.
But your algebra has to be defined in terms of gauge invariant operators, right?
Yeah, no, the point is right now, first I want to show that there is a modular, half-sided modular inclusion. I have not extended my algebra so far. This is just a quantum field line.
Okay, but so far therefore not
Yeah,
correctly.
this is just going to give me the modular Hamiltonian associated to the wedge function. This half-sided modular inclusions uses for that purpose. Okay, so let me actually just flash this. If you have a half-sided modular inclusion, what do you have? So what you have is a unitary operator of this form, okay, such that the wedge B is defined, the algebra at B is defined by U minus 1 A U1. Okay. And now you know what that U should be, right? Because you know what B is and you know what A is. B is related by a null translation from A. Okay. So you know that that unitary operator is actually just a null translation. So you can figure out what that unitary operator is. And that operator turns out to be this, where V star is the flux at which you want the black hole entropy. Okay. So then you can show that the modular operator of B is related to the modular operator of A by this null translation. Okay. So this is just a way of getting the modular operator associated with the wedge B. And this operator has the form of the generator of the flow of this vector field. And this vector field, V minus V star d by dV, has just the behavior of those people's construction. So if this is your wedge V star, then the flow of the operator is a modular flow like this. Okay, so it exactly satisfies that form. And we know that that is a modular Hamiltonian, so we can apply their entire analysis. So for finite regions, what they do
So
is
this modular operator is acts locally in that region?
Yeah, so the modular operator is geometric for this wedge. It's always right. It's the integral curves of V minus V star.
I thought that the same because there's a modular Hamiltonian acts locally on the null horizon, but
In their general construction, but here we have a situation where we are able to say much more because we are looking at wedges of the black hole spacetime.
so but even this operator,
Yeah,
integral of T,
yeah.
that operator will act locally on the null horizon.
All the Cauchy slots, yes.
On that null horizon,
Yeah.
right? But it may not act locally else.
No, it, what I'm saying is this operator acts geometrically everywhere in the situation where we are considering.
Why is it?
Why?
It just happens to be.
Why can you argue that again, please?
It's the modular operator. It's a modular operator for the whole
Not
region.
always do modular operators act geometrically, right?
Sorry, is V of Vy independent?
Yeah, V is actually, I agree with you, V is only defined on the horizon.
No, I meant to say if V was Y dependent.
Y dependent, yeah, V star is Y dependent, V star is Y dependent, can be an arbitrary.
That's not a killing vector. So.
No, V star of Y is an arbitrary slice of the horizon.
Correct.
Yeah.
So if.
This is not a killing vector.
That's
Sure.
right, exactly.
This is not a killing vector.
Exactly, so that operator will not act locally elsewhere.
Let me just think about it. I think in this particular case it does, but
Maybe
it's not given by this form, right? So that's difficult for me to figure out.
In general, we don't expect this.
In general, we don't.
It is only expected of
In
these
general,
very
we
nice
don't.
slices.
In general, we don't.
So why is it so nice here?
It is nice here, okay, on the black hole horizon, it's nice. Away from the black hole horizon, if
But
you
that
had
you require
curve, for
crucially,
example.
right? You require that crucially.
Yeah, you require that crucially. In the Schwarzschild case, it is completely true. Okay. In the curve case, it's not
No,
local.
it's a Schwarzschild case, it will be nice to understand.
Yeah, I'll just write this in the usual Schwarzschild variable and tell you.
What was Y in that exchange?
V star of Y is the cut. So suppose you.
Y are coordinates.
Suppose you take this. Yeah,
On the
suppose you take
sphere
this.
of the horizon?
Yes.
Yeah, so if the horizon is this null hypersurface, it's an arbitrary cut. Where these are the transverse coordinates. So V star is a function of the transverse coordinates.
Even if it's a constant, it would not be geometric, right? Or would it be
In that case, it looks like a killing vector, right? Like some killing vector field logarithm. So you can deform it away and like act locally and interact locally and everything. But I mean, if that V is Y dependent, stuff.
V star is Y.
Star is Y dependent.
Yeah.
Then.
Yeah, so what you're saying is when we write it in terms of the usual Schwarzschild coordinates, it will not be, what?
I guess I'm just saying that it will act locally on operators which are supported on the null rest.
Yeah,
But if you.
which is what I need for my
That's
calculation
okay.
actually, which is actually what I need for my calculation.
So what are we trying to do at this point? What is all this?
Okay,
discussion trying-
what we're trying to do, we have these wedges, okay, wedges of black hole space. I need to prove that SGen increases along this direction. Okay, so I consider these wedges, I will compare one wedge with a later wedge. And I will try to prove that SGen is increasing.
But
So
for
instead of, sorry, just to make sure, so instead of the original proof which had SGen at the bifurcate horizon minus
We
SGen
will get SGen at any arbitrary.
equal to relative entropy, here you will get
Yes,
between any 2 points along the
exactly,
graph.
exactly.
But for that, you can just have constant cuts, right? Why does there need to be Y dependent cuts?
You can put Y dependent.
That's
The
what I
proof
was
follows,
thinking.
the proof
So
follows for
then,
any
so then
arbitrary.
you mean then the comparison would happen between this Y dependent cut
And
and the
other.
cut that is strictly inside, is a
Yes,
partial or
exactly. It should
Not
be strictly. inside.
absolute.
Yeah, it should be strictly.
Well, I was also thinking you may just not want to have a Y dependence, but you perhaps want a more general state.
We want a more general.
Even if you break the spherical symmetry by stuff falling in, you can still.
So long as one region is completely contained in that.
And just to understand the structure, the right hand side, the semiclassics is clear, that is SGen. You want to prove this fancy, you want a fancy proof of the same thing. Hilbert space.
SGen, DSGen by DV,
You want a completely Hilbert space.
you want a completely Hilbert space. So what these people
What
do,
is clear?
There's the semi-classical, like that. If you don't think of areas coming from a Hilbert space, A plus whatever, entanglement entropy increasing, that's zillions of people, right? Starting at so so this is some to give a fancy version.
Essentially, the old way of thinking about it, at least when Wald's way of thinking about it, you paradoxically of relative entropy. If I understand your mind, you're now trying to.
we will also use monotonicity of relative
for this
entropy,
new one.
but for the new algebra,
In
so
fact,
the
straight.
various pieces will be all finite.
Just one along these lines, if you don't mind, just one. Change in area captures a huge amount of entropy. How are you getting that by just 1 degree of freedom in there? I'll maybe ask you later. First, we'll finish here.
Even in the previous case.
Yeah.
Okay, so what we have to do is to apply,
In square entropy.
okay, to apply this result to our case, what we need to do is we need to add an observer in each of these wedges. Okay, and then we need to, make a cross product algebra, do everything which these people did for these wedges. And then here is my algebra. So what I've done is I've added an observer. If you want, you can also add an ADM degree of freedom, which is not a cross product, but the observer is still the cross product with the algebra. Okay. And then we don't look at algebra entropy, we just look at relative entropy, but for the two extended states, phi hat and the extended Hartle-Hawking state, okay, where the observer degree of freedom is the same for both. And we take it to be a semi-classical state. Then we can show that for semi-classical states, the relative entropy between phi hat and omega hat is exactly that between phi and omega. So that tells you that even if you break up the relative entropy between phi and omega into pieces, each of those pieces gets renormalized in such a way that this relation is true. So I'm just giving you the relative entropy for phi with omega, but you can actually write the whole horrible thing with phi hat and omega, right? And pieces will just cancel out. So you have this relation for the relative entropy where this K is the modular Hamiltonian. And you have this between the state at phi and the Hartle-Hawking state. Now, if you implement the constraint along the partial Cauchy slice, then you will get an area term coming from here, okay, associated with the state phi. Now we can use this second equation into the first equation to write the relative entropy in terms of areas. And you see that because the relative entropy compares two states, all the observer and ADM degrees of freedom cancel out in a single direction. Then we use the fact that the Hartle-Hawking state is time independent. So this entropy associated with the Hartle-Hawking state can be evaluated at the cut V equals infinity. Then we also assume, as Witten assumed, that the QFT state is indistinguishable from the Hartle-Hawking state at latest. Then you get that the relative entropy is S gen infinity minus S gen at an arbitrary. Now you can do this for a later time, okay? And then you will just get from the monotonicity of the relative entropy that this is true, and therefore S gen V double star is greater than or equal to S gen V star. Okay? So you get a local GSL by applying these people's construction in a case where the assumptions are exactly true. Okay, so let me just summarize this part. There was a second part also, but we don't need to do that if there is not enough time. Okay, so let me just summarize this.
But we could have another lecture.
Yeah, so I'm here.
Whatever you.
Yeah, I'm here till Thursday, so it doesn't. Okay, so the generalized second law was proved by Wald under the assumption of a renormalization scheme for divergent quantities. What these people, Witten and collaborators, did was seen as supplying such a renormalization scheme. However, a local GSL was not obtained. So what we show is that we can obtain a local GSL and embed a Wald-style proof in this construction. And I didn't say anything for Kerr, but this works for Kerr as well, and for all asymptotically flat and asymptotically ADS black holes, modulo some technical assumptions, which actually have been proved to be true for slowly rotating Kerr. But what we need is them to be true in general for Kerr, and then we can do the same. So the modular Hamiltonian on the Kerr horizon is needed for this, just on the horizon, and that was obtained by these. So let me just end with some interesting problems, at least problems which I found interesting. One is that an event horizon is a teleological concept. So there are more local notions of horizons, such as dynamical horizons. Is there a GSL for such horizons? At first, I thought that the construction of these people would help in doing that, but there seem to be issues with it. Then,
Just to say, I mean, it's very usually not very easy to come up with a generalized second law for other horizons. Right?
for a dynamic
So
horizon.
if you were going to be able to pull it off, it would be a little strange. Right?
So dynamical horizon would be a space-like surface.
Yeah, so if
And
you
you
try a parent or these quantum.
Yeah, so
focusing
what I
versions,
was thinking was,
then you get just-
wedges like this associated with the space-like surfaces. Okay, but the problem is that you cannot use the construction of these people for these regions because you have to ultimately compare the answer you get here to the answer here. And that's very difficult.
In classical gravity, is not a second law for this.
Yeah, so that's what I'm saying.
Yes, there is a second law. There's a classical second law for.
But really for apparent horizons or any generalization, you typically.
I think it's there for Ashtekar and Krishnan's dynamical horizons. They have all the classical results.
Is for apparent or some generalizations thereof with entanglement seems very.
No, with entanglement, with fields put in is hard. Just
Yeah.
classical second law is true for the dynamical horizon.
I don't even know what that concept is, I see. Okay, but I thought it wasn't too easy. Okay.
Then Another question is whether if you go beyond the semi-classical approximation, are you going to get some entropy which is actually monotonic, and what would that mean? So could the algebra entropy be the relevant quantity that generalizes this generalized entropy beyond the semi-classical picture? Some people have done some work on that, but nobody has a general answer. Then there,
Just to understand, since you set up the problem as being something that would work for any Cauchy slice, any causal diamond,
yes,
the part of the argument which doesn't go through is that you don't have this analog of this scaling vector v minus v star d by dv.
this is for which problem? For the dynamical horizon?
I could just take a null ray.
Yeah.
Let's say I take a null ray,
Yeah, so suppose this is your dynamical horizon, this is like a space like.
I don't know what a dynamical horizon is.
It is a union of marginally trapped zones.
Oh, okay, so just over time, right?
Yeah.
Okay, yeah, that's what I meant by the
Yeah.
evolution of.
Yeah.
It's very hard to put in the quantum matter and prove it.
Yeah.
That's actually something,
Mhm.
yeah.
But even classically for apparent horizons, is there a second law? Classically,
There is a second law for these dynamical horizons.
There
are they the same as apparent horizons?
They are the same as, they are like a union of
Yeah.
apparent horizons because you have marginally trapped zones. Yeah.
There is, huh? So I thought there wasn't, but.
There is.
Yes. I'm not remembering now, yeah. It just the Raychaudhuri equation coupled with the whatever weak, whatever energy momentum properties. Null is enough, huh? Is enough.
Yeah.
Okay, maybe that's true, I have.
Then the last problem which I just wanted to mention was that, is there an algebraic way to describe the entire evaporation process, the information loss, information recovery? There is a paper by these authors where they claim to do all that. But the problem is that all the constructions used are specific to type 2-1 algebra. But what we saw was from the cross product, we got a type 2 infinity algebra. So it's unclear how the construction generalizes to this case. So I just want to leave these questions. So should I continue tomorrow, or do you want me to, it will take me about some 15 minutes or something to finish this.
We had Emma at 11 o'clock, right? Yeah.
We will start on Thursday.
No, but 15 minutes if she needs.
We do it now.
Yeah.
We can do it till 1? Okay.
I mean,
By the way, just one question before that. So, when you talk about this general regions and general diamonds, there you have this observer, and this observer needs to move along with geodesic, right? You want everything to be a solution, I would imagine.
You want everything, why should the observer, the observer will move along with geodesic because, sure, observer is like
And
a
the
free
mass
particle.
of that observer is not important.
It's not important in this particular construct.
Meaning-
You just think of the
I want to
observer as
find
giving you a clock.
So it's a zero mass.
No, it is the Q that you add to the Hamiltonian is the energy of the observer. It has to be greater than or equal to 0, that you have to put,
Okay.
that's a subtlety which I didn't talk about. But apart from that, you're not expecting anything more from it.
So if it is heavy enough, it will back react also, right? Then you would have to,
Yeah, then you will have to consider.
I see. And
So the Subrat has a paper, right, where he has a picture of what is the observer in ETS-CFT, and he has some ranges for the mass of the observer. So it cannot be too heavy.
also in this proof that you gave about this, becoming this diamond then becoming smaller and smaller and smaller because your cut kind of
Goes later and later.
include, goes later and later and later. So there you want to argue in the same way these other guys argue, right? For this arbitrary diamond, you want to use their proof.
We
So
want
in
to,
particular-
but we, in our case, all the assumptions turn out to be exactly.
Right.
They have
But
some
in-
assumptions.
But in particular, you want this observer also.
You want an observer.
So. but
Without
you-
observer,
so
you
this is
cannot do it.
probably
But the
something
observer
technical.
degree of freedom cancels out when you're trying to compute the
No,
GS.
but this is just, I want to go back to my initial comment that I had, that if you have an observer and you consider its domain of dependence, it will limit the kind of cuts you can get,
Okay.
right? Geometrically.
If you think of your observer as a world line.
Yeah,
If you think of your observer as a world line,
so that is not needed.
Yeah,
It can be a
yeah.
sheet or whatever,
Yeah,
it can
and-
have any.
yeah. It can be any energy momentum which is non-zero in proportions. on all the Cauchy slices in your wedge.
So then you can construct any.
Yeah.
Or are there still be some convexity conditions that would be,
I
that
don't
would
think-
be, that would need to be imposed?
I don't know. I didn't impose any such condition, but if you think there's an issue with that, just tell me.
I mean, I'm just wondering, because if you have, that if you want to have any observer, but maybe, some concave region may not appear.
So I can ask a general question. I mean, part of the arguments seem very physical but made precise. Parts seem hyper-technical. I can't put. So part which seems sensible is if some region of space-time, okay, take a causal diamond. If you have a sub-algebra of physical operators, gauge invariant operators in that region, all operators, then the entropy you assign to it is the generalized. Okay. But this seems very sensible. To make that notion of gauge invariant operators precise, you introduced one observer. But that was just a way to make it precise. As Shiraz put it, I mean, that observer could have one L2 worth of degree of freedom. It's not as if the generalized entropy is the entropy that observer can possibly see or imagine, right? But it's not. It just that observer's role, as Onkar also emphasized,
It's for the
is to
dressing.
make
It's
the
for the
dressing. Okay, so you need some way to make the. Okay, so that seems fine. But then when you try to when you try to make it precise and so on for some second law, you need all kinds of things about the inclusion, all that. Which where I'm going is, in the end, if you have a sub-algebra of physical gauge invariant operators, then it should have less relative entropy than the full algebra. Can't you just say any
You
dressing?
unpackage the relative entropy into its pieces, right? In order to prove that.
Can I not just say, as long as I have a way of defining physical gauge invariant operators, okay, introduce your observer of choice in the causal diamond of interest, it will go. Okay, can I not just say that in general for any space time? And then not have to worry about the details of some.
No, the details were actually required to get the modular Hamilton. It was required to prove that in these people's construction, whatever assumptions they made were true. That for that we require.
So in other words, the more.
To compute the modular Hamiltonian is hard, very hard.
But you
So you
need
need
that, isn't it? It's not enough to say if I have.
No, because you want to do the cross product by the modular automorphism.
So this is the hyper-technical part of it. So it's not enough to say, have a dressing. I mean, have some fiducial observer which provides dressing. Then there's some hyper-technical part, which is, but then you need to be able to define a modular Hamiltonian in the right properties. Oh, why is that?
This cross product construction in the previous case, they will use, the explicit construction used that. Right?
Yeah, you needed
Dressing.
that, right? In order for you to.
Explicit form of the dressing.
In order to make everything finite, you need that. So you need to go to a type 3.
Could I also ask one sort of general question? If suppose we're in ADS-CFT, we have some energy, and we change energy by order 1. Now, say I change the black hole mass by order. Now, black hole entropy is n squared times f of E by n squared. So I change by order 1, the n squares cancel. Because the Taylor expansion is 1 by n squared. And then you get an order 1 entropy. Are these the kind of energies we're looking at? Then I can sort of understand that adding a new degree of freedom can add a new order 1 entropy. But I mean, the real miracle in gravity is that you change an area by this much, and it changes the entropy by n squared, which is some huge thing, which doesn't look like it could come out of quantizing anything. So if we're limiting ourselves to small fluctuations like energy order 1 around black hole backgrounds, then I can understand that this kind of.
Yeah, in the semiclassical state, you're doing that. Right? In the semiclassical state, you can think of as, just small fluctuations of the geometry.
Yeah, but there's a much bigger question, which is that you can change the mass from 1 to whatever. That 1 degree of freedom parameterizes some huge entropy. That doesn't look like it's coming out of quantizing anything. This doesn't throw any light on that.
That was in this C constant. This large entropy was in this constant C.
Also, see, I'm saying just black energy.
Yeah, there was this
See.
all that. So only differences could be addressed from
Yes.
this
Yes.
method, not the absolute value.
But now I'm confused. I mean, at least when you do the bulk derivation of the generalized second law, you can have a black hole which loses half its mass.
Yeah.
You know, and the entropy can change by order n square, and you have a second law, generalized second, right? So these
results are all is a order G calculation, order G.
No, that is also, oh, so you mean the moment you have the mass change in any equation, this breaks down?
Yeah, back
You need
reaction.
the background of this black hole,
Yeah,
small
yeah.
fluctuations.
Yeah.
And I really think order one energies and equals for you.
Well, that's very important point. You see, otherwise this doesn't go through. That
Otherwise,
will-
this, none of the Wald style proofs, nothing.
Because we should be suspicious that you can produce the entropy of a black hole without having the gluon. No? You sound it very small things, but not really.
Okay, so let me actually just continue. Okay, so I'm going to continue to something which is completely different,
Generalization of the original second.
which is called subalgebra subregion duality. So this is in the idiosyncratic setting, where as we were discussing yesterday, there is an emergent type 3 boundary algebra in the n tending to infinity limit, which is dual to every causally complete region. This is the proposal of these people for several years. This algebra is generated by single trace operators, and bulk features of spacetime regions such as light cones, horizons, crustal time can all be described in terms of algebraic properties of the emergent type 3 boundary.
Yeah. Okay, so subregion, okay. This was a emergent type 3 to every IC. This you're going to show this. So
No, they show it. It's very long.
Type 3, 1. So type 3 and then there's within type 3.
No, the type 3, 1 you can ignore. That's
Okay.
related to the spectrum of the modular operator.
Okay.
Every quantum field algebra is type 3, 1. So you
Okay.
can just bother about
Okay.
that, not bother about that.
And features is emergent, right? So this
And emergent, as Shiraj was saying yesterday, like if you look at all the correlators and you take the n1 to infinity limit.
oh, this is the generalized free fields.
Yeah, generalized free fields. Yeah, this is a generalized.
That's what we.
Yeah. Okay, so all these geometric properties of the interior can be described in terms of properties of the emergent type 3 algebra. And what these people wanted to do is Gesto and Liu. They wanted to look at horizons in the bulk in the limit where the 't coupling is finite and not infinite. Okay? So when the 't coupling is finite, the string length is also non-zero. And basically, they wanted to look at what is the geometry that the string of finite length sees. Are horizons, for example, a well-defined edge? And what they did was to propose a diagnostic for the presence of a horizon in the bulk at finite length.
But infinity.
Infinite n has to be.
So why is it a diagnostic of horizon that excitations die out exponentially?
I'm sorry.
One point for that you have an excitation, it dies off exponentially. Isn't that a good diagnostic for the horizon?
If you have an excitation. Okay, what they have is a geometric.
2-point functions are
Yeah, 2-point. It is related to 2-point function. Find it.
Okay.
Exponentially,
Decaying time.
with what exponent of them?
With any exponent, any non-zero exponent is important. I mean, because the global ADS it would not.
Okay, so what the diagnostic is you look at the black hole and you look at, say, one copy of your thermal ADS, and you look at you basically look at wedges of this sort. Okay, so you're going from minus T0 to T0 here, for example. You have a time band algebra in the boundary, and you have a diamond, triangle shaped region in the boundary. And you do the same thing for thermal ADS. Now,
Time band algebra, because equation of motion only gives you a constraint after you go time pi.
yeah, that's what you're going to, exactly what it is. That's a diagnosis. So what they're going to define is that, if you have a thermophile double state, then the causal depth of this state is the largest value of 2T0, for which the time band algebra is a strict subalgebra of the right. So let's go back to the figure here. You see this diamond shaped region or this triangle shaped region. Okay, the time band algebra that's associated in the boundary to this region, is that a proper subalgebra of the full algebra of the right? Okay, this is the right ADS piece, and this is the right exterior for a black. you can see from here that only when T0 goes to infinity is this the full right algebra. It's always a proper subalgebra in the black hole case, but not so in thermal radius. Thermal radius, if you could take these times to be large, then after some times pi would.
Because in the black hole case, you can have data that comes from the past singularity that comes to the horizon, and you won't see it until you go to infinity.
Exactly.
How is it? I didn't understand. In the, in the black hole case, yeah, you can get stuff from the singularity hitting that boundary.
Hitting the boundary, and then you localize it to the horizon, so it only shows up at very late time. So if you know the solution on the boundary at all earlier times, you don't know what's going to happen in later time. But in ADS, we know that there's a periodicity of time, periodicity of 2 pi. So if you know over a time of order pi, then you know it forever.
You know it forever. So what, okay, thank you. So what does that correspond?
Yeah, so what they're going to say is that if you have these types of time bands, and if the algebra associated to that time band is a proper subalgebra of the full right algebra.
But that it is, right?
Then you will always have a horizon.
But I think they're going to distinguish thermal ADS from black hole.
Yeah.
Yeah. But in the thermal ADS also, if you had a small.
Small enough, then.
There's a limit at the side.
Yeah, there is a limit.
They're distinguished. Okay, I'm so sorry again. Okay.
So you say that there is a stringy horizon in this case, in the state, if the time band algebra like this are strict subalgebras of the right algebra. This is their diagnostic for the presence of a horizon in the bulk, and it is related to the 2-point function for various fields. So it can be computed in the boundary algebra, and they computed it for some examples, and it can be different for different boundary operator algebras and therefore bulk fields at finite. Now,
how do they compute a finite level?
so they use this, this 2-point function. So what they do is they say so let me just go here. So suppose you have let's say you have a black hole and you have a time band algebra. Okay, then this algebra has the operators here have a commutant, which is this. There is a relative commutant, which is that part of the commutant which lies in the right algebra.
So are we doing the black hole case?
Yeah, we're doing the black hole case. Just explaining to you the black hole case.
Yeah.
So you have this relative commutant here.
Mm-hmm.
So you just ask, is there some relative commutant in this algebra? Is there something which commutes with the operators here?
Yeah, the region near the.
Yeah.
I thought that your worry was that because the finite lambda, the strings are large,
Yeah.
that you can't use these locality diagrams. I thought that.
So what they are doing is they are trying to give a diagnostic of a stringy horizon entirely in terms of the boundary algebra.
No, I understand. But,
So they say that the stringy horizon is this causal gap.
okay, so there's a conjecture which says that even at finite lambda, no matter how small,
Yeah.
that if this time band algebra keeps increasing as you increase the time, then that's the horizon.
Then that's a horizon.
Okay, but
Then you would say that there's a stringy
yeah,
horizon.
it sounds very reasonable, but just to ask, you might worry that when strings are about the size of ADS, this breaks down, right? Because everything is very non-local.
Yeah, it should.
Is there a check?
No.
There is CFD calculation for this?
There is a calculation which relates the causal depth to the 2-point function of any operator that you want to take in the boundary. So there could be different causal depths for different fields.
But all these words, causal depth, etc., for finite lambda, what has to be?
Yeah. One is assuming that they hold for finite.
But that's the whole point of finite.
So you have
locality is breaking down, right? So
But okay, no.
But again, even in large lambda, this is a good diagnostic, let's say. Then can we, so at least in large lambda, one can see this explicitly.
Yeah, one can see this explicitly for several
So in
examples.
CFD, what sort of calculation am I doing in some thermal state? When low temperature.
Thermophile double state, you can take different states.
Okay.
And you can do this calculation, it's related to the spectral function
Okay.
of that operator.
I think it's basically the fact that if you know the expectation value of the operator over a certain time, it doesn't determine it in the future. There's no equation of motion. That's basically it.
No, but how do I compute?
How do you actually calculate
it at large lambda?
You could calculate perhaps. I mean, what you can't actually calculate it, but what calculation would you do?
Yes. And then what is the support that I offer for this? That at finite, a smaller temperature below talking page, I see this behavior and then
You can do it
this
from the
behavior.
bulk. From the bulk.
No, not from bulk. I mean, I want to do just in the CFT.
No, they are doing it in the CFT.
Yeah, how would they
So I think they look at the spectral function, look at various possibilities for the spectral function. Okay, is it,
function?
okay, so rho, let me just write. Rho,
Integrate.
some OT prime,
Two-point function, but omega.
yeah, and then you go in omega space. Okay, and then you have some assumptions, is this spectral function having compact support? Is this spectral function having support in all the real values? And then you are able to compute this causal depth for each of those cases. And then from there you get that for thermal ADS, the causal depth is finite, and for black hole it is.
But at large lambda, how do I do this?
So you calculate from it. There's a one. You calculate this 2-point function from the bulk.
Okay, fine. Then I guess then you would see that anyway, right?
We might be a little better by saying something like it's a sparse CFT and
Yeah,
you
some
know, you have some, yeah, it might
Low
be
temperature, you can. High temperature, you can't. You don't know how to reproduce the entropy, right? Like entropy. So, no real chance.
Well, I mean, we don't
modular
want to
transform the.
You produce the.
ADS.
Yeah.
That's fine.
I think he would be happy in any. You might be able to pull it off. You might be able to.
Just to see that explicitly.
I don't know enough, but it's not.
ADS we can compute 2-point functions. 2-point functions are at finite temperature completely determined by conformity. So then there's no.
And then you should be able to see that.
Oh yeah. Because you just take the 2-point function and see the spectral formula.
But do you put in that you're at real time finite temperature, right? Somewhere you.
Finite temperature. You just do a modular.
Yeah.
So
So real time finite.
yeah.
Okay, so what is the,
Where does lambda? It will enter only the 2-point function will not enter. It's completely determined by conformity. Yeah. This is an example of the general rule that ADS is not as interesting as ADS deflates. Yeah, higher point function. Yeah.
okay, so how do we understand from the bulk that different bulk fields have different stringy horizons in the bulk picture? So then you see that if alpha prime is non-zero, there are higher curvature corrections to understand gravity. And of course, there is some subtlety regarding the order alpha prime square correction because you can do field redefinitions which push some terms to higher order in alpha prime. But what happens in higher curvature gravity, it's known that different polarization modes of the graviton also, for example, can propagate with different speeds and they see different effective metrics. So I just wanted to say these things to make a connection with some recent work which we have done, which was not motivated by this problem, but also can be applied here. So since it's already one, I will just summarize that. So what we showed was for a large class of higher curvature theories, which are quadratic in the curvature, we showed that the different, although there may be different polarization modes of the graviton which see different effective metrics, they all see the same horizon. They all see the same killing horizon. And so that these were some slides about that, but let me just go to the last.
Wait, so that is a classic result in classical.
It's a result in classical gravity. So it has already been done for Gauss-Bonnet gravity by Real, and we did it for arbitrary Riemann square, Ricci square, Ricci scalar square terms.
So this is the expectation that comes is from this finite lambda analysis that you want a finite lambda.
So what
That you should see
these
the same
people, Gesto and Liu, argue that you should see the same horizon for different fields. And what we see in the bulk is just by doing the higher curvature gravity calculation, the different modes of the graviton see the same.
Would this also be true dynamical situations?
Dynamical situations, let me just think.
Collapse, formation of a black hole. Would it then be true that different modes would see the same horizon? Not only for.
Okay, we have not done.
I mean, surprisingly.
We just did perturbations over some arbitrary background in these higher curvature gravity theories. We did a characteristic analysis and concluded.
Sounds interesting.
Say that. It's surprising.
Because in a general, certainly as Suneeta said, in a general case, things are moving at different speeds. Now, if it's time evolving, there's nothing very special about it.
Special about it.
The horizon.
There's no bifurcation.
Yeah. It's that the killing that in a stationary situation that the many different metrics say the same is somehow inherent to this Wald kind of thing, right? Because if you had no horizon according to what metric, that would be the starting point of.
Usually the second law uses the Einstein frame, right? If you don't use it, you don't have a second law. So there is a clearly preferred.
But suppose I redefine my metric. Metric was metric plus G army. Then what? Einstein frame in which metric?
Oh,
Because you're looking at high derivative correct.
okay, I don't know the second one.
Yeah.
I don't know what the story is there.
But Wald claims, at least claims to have a first law, and then you can try to prove a second law. And just in order to begin this Wald formalism, you have a metric, and you have a horizon. And it had better be that there's some universality about the horizon, at least in stationary situations. Otherwise, what are you talking about? In which definition?
In this
So the
stationary
stationary
situation,
situation,
how does it come about with symbol?
this is something I once knew, but Suneeta Vardarajan.
So what is the question?
In the Wald formalism, stationary situations, presumably there is some universality of the horizon under field definitions.
But I wanted to ask you about that, Suneeta.
Yes, there is.
There is.
You can argue that.
Yeah.
Suppose you take, field definitions like G mu plus R mu.
Yeah,
You can certainly argue.
you can argue that.
Yeah,
Right?
if you had a killing horizon to begin with,
Yeah.
there will be killing symmetry if you add to the G mu something else which depends on the
killing
geometry.
symmetry
Yeah.
tells you that.
The killing symmetry will be there.
Right.
And the bifurcation surface will also be preserved.
Right. So now if you're staying near to that, it's less surprising. But if you go very far away, it seems crazy. Right? Yeah.
Sorry, I seem to remember this probably wrongly that if I just do scalar fields, then depending on the kind of coupling, I don't necessarily always agree on where the killing together, right?
Yeah, so I have not done non-minimal, not thought about non-minimal.
I thought that was the case, and maybe I'm wrong, but that's what I see. I mean, in other words,
You could have.
is this like some journal?
Yeah, so actually this is, no. So it is actually surprising. If you just start doing blindly doing the calculations, it's surprising that you get the same horizon. Because your gravitons do propagate with different speeds, but they all see the same price. So I think if you had a non-minimally coupled scalar field or something, it will be quite complicated.
That's what I vaguely
Yeah.
remember. I could be wrong, but there's someday recollection.
Yeah, it would be quite complicated to find out what are the characteristics.
Certainly higher derivative case.
You expect.
I think. But two derivative I thought would be.
Yeah, would you Two there with all additional couple R files or whatever. Okay, anyway, yeah, I see.
Yeah, so I'll just stop here. That's all I'm.
Okay.